So I will highlight a few projects. If you want to talk more about them later, then send me a message. Or if you want to talk about anything else again, get in touch. So very briefly, essentially what I do is combining a bit of engineering, a bit of economics, and a bit of operations research to have models that combine representations of the physical systems with economic incentives. And what we can do with that, for instance, and I'll give you examples of each of these categories, is investigate what happens if you have a lot of renewable integration. So what happens to prices, what happens to consumers, what happens to profits of incumbents, etc. You can use the models to optimize decisions. Again, I'll give an example of that. And you can also use it to simulate what would happen if you change the rules of the game, if you change the market design. So what I'm particularly interested in is, first of all, working on the kind of economic part of techno-economic modeling. So there are a lot of, I guess I'm talking mainly to an audience of engineers, so I might now insult you, but I think there are a lot of engineers working on these types of models that tend to focus more on the technical, getting more technical detail in. What I'm interested in is making sure the economic detail is at the same level. So that includes things like strategic behavior by investors or by generators or even by large consumers, looking at effects of uncertainty and attitudes to risk, things like risk aversion, and looking at the way markets actually work. So they're multi-stage processes that we need to take into account. So that's my main interest. And then I'm also interested in specific applications of these models. And I'll give an example later. So here's my first example, which is about Spain, because since we're talking about Spain, I thought I'd use this example. Where we set up a model to investigate the effects of specifically rooftop solar in the Spanish market. And there's a paper co-authored by David Ribo Perez and Carlos Avares Bell from the Politécnico de Valencia. If you want the paper, then send me a message after this. Now, this is now about a couple of years old. The motivation for this research was essentially what someone is talking about in the parallel session at this exact same time, is the Spanish government's temporary, luckily, negative attitude towards solar energy, where at least for a time, there were actually taxes on solar energy rather than subsidies. This has now been reversed, but this was the motivation for this paper. And our question was essentially, since there appears to be quite a lot of lobbying, or there appeared to be at the time quite a lot of lobbying to the Spanish government to make sure that distributed solar was penalized, we wanted to understand who actually loses or who actually wins from distributed solar. So if we can answer that question, then we can maybe understand why people are against this or in favor. So what we did for this is we set up a model of the Spanish network. It doesn't have the full network in it. We aggregated regions, but we do have a physical network in there. But instead of looking at the system as a whole, we look specifically at the incentives of individual firms. So we have a model, a Nash-Gounod model, so we allow firms to exercise market power, which is an issue in the Spanish market. Generators have been fined for exercising market power, so we can say fairly confidently that this exists. So we need to model that. And we also model demand in a little bit more detail. So we have demand that is price sensitive. So consumers will buy more electricity if the price is lower. And we look at, if you see here on the right, we look at all of the individual large players, and the smaller ones are aggregated into one unit. The eagle-eyed among you will spot that one of these companies has now changed names. So we have a physical model, and then we have an economic model, which takes into account the fact that there is imperfect competition. So prices are not necessarily based on costs. They are based on strategic decisions made by generators. So if we run this model, we can generate figures like this. So this, for instance, is for a typical summer day, the reduction in generation for each of the major players as we increase the penetration of solar self-generation. And what we can see here, for instance, is that there are some players who are not affected very much. There are some who are affected a lot. And we can then look at what the effect of that then is on profits for these generators. And again, we see that some of them lose a little bit of profit if we increase self-generation. Some of them really lose a lot. So if we know this kind of distribution, we can start thinking about which companies are probably most vehemently opposed to higher subsidies for solar rooftops. They'll be the companies who are kind of here. Some conclusions we can draw from this. So first of all, the impacts of solar on incumbents' profits can be major, but they are far from uniform. The reasons that you see these differences is that so incumbents have different existing generation portfolios. But another reason is that some of these companies currently have much more market power than others. So some of these companies are able to act strategically to generate profits that they really shouldn't be making. And some of that is lost if we increase the penetration of solar self-generation. So there are two effects of increasing this penetration. There's a merit order effect, which we all know about. If we increase the amount of zero marginal cost renewable generation, then the price will decrease. So that's the reason that all of these curves are going down. But the reasons that some of them are going down more is because some of them also lose market power because net demand reduces. So what we say in this paper, essentially, there are desirable and undesirable effects, quote unquote, of increasing the solar penetration. So there are effects on profits that are desirable because they reduce market power. And there are some effects on profitability of incumbents that are maybe worth thinking about a little bit more. So there are merit order effects, which the companies have a kind of genuine case to argue against higher subsidies, but these market power effects, we really shouldn't worry about them too much because that means taking away profits from incumbents that they shouldn't have been making in the first place anyway. Also, we find that if we include demand that reacts to prices, then this whole thing is not a zero-sum game. If we increase distributed generation, that doesn't mean that the incumbents generate the same amount less that I now generate locally. Because prices decreased, energy consumption goes up a little bit as well. So it's not a straight case of solar distributed generation versus large-scale generation. There is, but the total pie gets larger as well. So these things, we need to really understand these things if we want to understand the public debate around the desirability or the effects of solar self-generation. And we need to know what the effects on the individual incumbents are, and we can do that with these types of techno-economic models that include a lot of economic detail. So that was the first example. Second example is more about optimizing decisions, and this is an industrial example. And again, there is a paper which is co-authored with a number of researchers from EDF, large generation owner. The motivation for this particular research was we were looking at wind measurement campaigns. So they cost the developers quite a lot of money. So figuring out what the resource is at the location that you are thinking about bidding for or that you're thinking about developing costs a lot of money, and you have to spend that money long before any revenues come in. Now, at EDF and also generally in the industry, before we did this piece of research, the kind of general opinion was that better wind resource data is always worth it. So put a met masts in for as long as you can to make sure you have a really good idea about what the wind resource is at the site that you're interested in. That's always worth it. The main reason for this is that if you have a better idea about what the wind resource is at a particular site, you will be able to get cheaper finance for your projects. If you go to a bank saying, I'm really sure that this is what the wind resource is, there is less uncertainty about this, and therefore they will give you better financing conditions. But as I said, this measurement is really expensive. So we were wondering about whether instead of always trying to go for the best data quality, it might make more sense to optimize the data quality. So that's the question. Is better data always worth it? And how do we optimize data quality specifically for, in this case, offshore wind? Slightly different type of model here. So not an equilibrium model or an optimization model, but a relatively complex series of models that EDF was using in-house to determine the costs of financial metrics of projects at a particular site. So it has all these different components, which I'm not going to explain. We changed this model to add stochasticity in, and we changed the model a little bit to add in detailed project finance constraints because they turn out to be really important. So what can you do with this? So first of all, you can look at this theoretically. What's important to realize here is that if you go to a bank asking for money to finance a particular offshore project, at least in the way EDF does it, the bank will generally give you more funding, so a higher gearing rate, so they'll fund a larger percentage of the project if there is less uncertainty. So if I reduce my uncertainty, so I'm in the bottom left graph here, if I reduce my uncertainty, a bank will give me more money, and this reduces the cost of my project. However, if I reduce my uncertainty, also my development expenditure increases because I need to go for more expensive measurement technologies or longer measurement campaigns. If I take these two together, I can get a graph of the kind of levelized cost of energy, which is a metric, as we discussed earlier, I don't like, but in this case, because we're looking at individual projects, I think it's justified. The issue is that banks will never finance more than a particular fraction of the project. For offshore wind, that might be 75 or 80%. So once you've reduced your uncertainty beyond a certain point, further reducing it does not decrease your finance costs further. So from this, you can immediately see you should never go beyond this point in reducing uncertainty. So better measurement campaigns are not always worth it. But it depends on the kind of projects that you have. So we looked at a couple of real world projects. These are very complicated figures. But basically what you can look at here is we have 3 different projects. They're actual EDF projects. I'm not allowed to tell you which ones. So there's a project with a low wind resource, one with a high wind resource, and a kind of average project, a baseline project. And on the left-hand side, you can read the total LCOE of a project for a number of different measurement techniques. So we have the cheapest technique being mesoscale modeling, but that, as you can see, does not lead to the lowest LCOE because if you use this technique, there is a lot of uncertainty about your wind measurements, and banks will not finance a large fraction of your project. The most expensive ones are met masts. But again, they do not lead to the cheapest project. In this case, for the baseline project, it's the LiDARs that come out on top. So not the best data quality, also not the worst, but something in the middle that gives you a good trade-off between getting good project finance, but also not spending huge amounts of money on development. And for the low wind projects and the high wind projects, in this particular case, for this particular gearing rate, maximum gearing rate that we've assumed, again, LiDARs come out on top, but the order of the other technologies is slightly different. Okay, so conclusions from this is better data is not always worth it, especially if you've got a very high resource site and you can optimize data quality. So I've got a third example, but I won't go into this in detail. What we are looking here is the impact of risk aversion specifically. And again, there is a different type of model, and I'll just show you this. So this is a very complicated economic model with 4 different stages, which model everything from network investment, generation investment, to spot market trading, to redispatch. And again, we can use these types of models to figure out, in this case, what the impact of risk aversion is. And we're seeing that is quite major. And again, that is something that therefore needs to be included in any assessment of effects of policies or the potential amount of renewable generation that we are that we want to see. So the conclusion from all of this is, I guess, depending on your question, there are a lot of models that you can look at. I think in techno-economic modeling, we should put a little bit more emphasis on the economic side of techno-economic modeling and make sure we have these models that can actually capture the detail that we need. And that's something I'm very interested in. So if you are too, then get in touch.